Welcome back, everybody. Hope you had a good weekend. Get started. I still don't have the lecture from last week uploaded. I was sick all weekend long and gone yesterday, so I will get those up and update the notes as well. But there are notes on the currently, so you're not like completely left out high and dry, and there are videos. Just not the lecture videos that you've received normally, but they will be posted. Continuing on with chapter 7. Jumping from 7.1 to 7.2 now. Just kind of as a reminder, remember 7.1. Okay, central limit theorem. Okay, all it's really saying, the central limit theorem, and all we're doing in chapter 7 is literally saying, hey, I'm going to give you some formulas. These formulas you're going to use later on. Okay, you're going to use them all over the place in chapter 8, chapter 9. Did we do chapter 10? I don't think we did chapter 10. Anyway, 12, whatever. Okay, these work. They have to, because if not, we're just pulling stuff out of thin air, and who cares? No, they have to work. Okay, and so right now, what it's saying is, hey, when we do these things, and I give you these new little like formulas, they work so that way everything we do in the future, okay, post chapter 7, we know these are pretty reliable. Okay, so what you're going to notice in a lot of this is it's going to be the same stuff you've been doing. You're going to be finding, standard deviations. You're going to be finding z-scores, but the formulas are going to change now. Okay, because we're changing from populations into actually doing statistics now. Okay, remember, as I was talking to my son this morning, he was showing me some stuff with the schools, and I was like, I still don't understand why they're doing that, because you're dealing with a population. There is no reason to do what they're doing. Remember, when you're dealing with a population, there's no reason for any of this, really. Okay, because the math is concrete. I know everything I need to know about you as a class. If I just want to talk about grades, numbers, even age, demographic, I already know it. It's all here. I have all that information. But it's if I don't know all of you, then I can go, well, let me just take a sample of this. That's when things start getting a little weirder, right? Because we don't know everything. That's how come we start talking about inferential statistics. Okay, you make inferences. When I take a sample of something, okay, a large enough sample, which is what the central limit says, the population probably does not approach a normal curve. Okay, but when I take a large enough sample, that will approach a normal curve at times, depending. We'll talk about that later. And when it does, I have all these statistical tools I've given you up until now to do things with. Does that kind of make a little bit more sense? Kind of how things are going. Okay, so now we're going to do what we call a central limit theorem with means. Okay, and what you're going to start noticing in class is this, and it's going to help you, I promise you, especially as we're getting closer and closer to our final. And I uploaded your final yesterday. Okay, your final will be done on your computer, but instead of doing it through Canvas, you're going to be doing it through Hawks. Okay, in class, but through Hawks. So everybody will get the same question for number 1, but every question will be randomized. You know how Hawks does it. It says, hey, you may have these two right here will have the same exact question, but the numbers are going to be totally different. Okay, and where one might be less than, the other might be greater than, just depends. Okay, you've all done Hawks. I feel like it's going to be a little bit more intuitive for you to understand. Okay, you'll still need to turn in your paper, written homework, or sorry, written work on paper, so that way I can see your work and go, hey, you know what did you use on your calculator? Okay. Having said that, I want you to start realizing the pattern. If you start realizing the pattern now, 1, it's going to help you study. 2, it's going to help you kind of know what formula do I need to use. And by knowing what formula, I either know what calculator button do I need to use. Okay. Everything's going to go in this way. 8, 9. I'm going to show you something, just like I've done with central limit theorem. I'm going to show you something. Here it is, central limit theorem. And then I'm gonna say, hey, now let's do it with means. Here you go. And then I'm gonna say, now let's do it with proportions, percentages, remember? And that's exactly how everything's gonna go. I'm gonna show it to you. We're gonna learn it with something. We're gonna do it with proportions. And then at the end, we're also gonna do it with variances. Okay, moving forward, we won't do it with variances for this one, but we'll do it with variances as well. Every single time it's gonna be that order. Boom, 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 boom. Okay? And then you'll know, you can look at the question and go, it's dealing with standard deviation or variances. I know I can at least narrow that down to the last part of the chapter. In either this chapter or this chapter. One of these two, you know where to look. Okay, when you start working on your review and stuff like that, okay? Try to help you out a little bit. I don't think, I'm lying, I think one question in your whole of in your review comes from, or your final comes from chapter 7. Most of them of your final is going to come from chapter 6, 8, 9, and 12. Okay, 12 is super easy. You'll love 12. 12 will make you mad. You'll go. Okay, it's like intermediate algebra. It's literally learning slope. Okay, it's literally learning slope again. It's called regression. It's literally like, remember, a positive slope goes up, a negative slope goes down. Kind of like you're like, oh, that's it. Yeah. Except we learn where to put them. Like you have a whole bunch of data that looks really weird. You can say, well, is everything working for me or against me? You can go, oh, well, I put in all this data. It'll say, oh, look, it's going up, even though it's really kind of hard to see. Okay, it's kind of neat, you know, because sometimes regression models are hidden. Okay, so I'm a nerd. That's how come I think they're cool. Maybe you will too. Okay. Anyways, let's get started today. We'll get through 7.2 and we'll start on 7.3. Next class, we'll finish up 7.3 and do 8.1. Okay. So look at that. Not need to know that. Got some new formulas here. You don't look, you're going to be able to have, now mind you, you're going to get, okay, a formula sheet. I promise you, you will get a formula sheet. Okay, but I do need you to remember, I can give you all the formulas in the world. That means nothing if you don't know what they mean. Okay, also, and this goes for everybody online, so pay attention closely. Okay, these have to be turned back in. You are allowed, for my final, okay, a 3x5 note card. Okay, that's a 3-inch by 5-inch, and I'm specifying that because there's always gonna be that one smart that goes, I bought a 3-foot by 5-foot, you know. Okay, you're allowed one 3x5 note card. Okay, I don't care what you put on it. Put whatever you want to. Now, mind you, I give you the tables, I give you all the formulas. Okay, so hint, hint, maybe not waste your space writing formulas down on a note card. I promise you, I'm giving you every formula post chapter 5. Okay, like I'm not going to give you the binomial formula. Okay, I'm giving you everything you've learned post chapter 5. I'm not giving you Z. I'm not giving you this one either. The Z score. I don't think I gave you that one. Should have done that one enough. Now you got it memorized. Okay, but I will give you like this one. It'll be on there. Okay, doesn't really help you if you don't understand it all. I mean, you can look at it all day long. You might as well be reading Latin. Okay, or Greek. Okay. Okay, so there's that. Now remember, you need to go ahead and still remember how to parse things out. Okay, remember that the U, okay, down. Do not forget that U is also the same as what? The sample, okay? We will move away from this symbolism for this. This will eventually go away. Okay, I want you to kind of be warned of that. Right now, remember, central limit theorem. I'm proving a point with the central limit theorem. When we actually start doing statistics in chapter 8, I will no longer be saying, hey, the mu is equal to the mu of x bar. No, it will become x bar. Okay, so if you can kind of get in your head now that the mu of x bar is going to be the same as x bar later, you'll be like, okay, we're doing the same thing, same formula. It's just no longer is it proof of concept. We're doing concept. Okay. Also, don't forget, you also have a standard deviation, but it's not the standard deviation anymore, is it? Okay. the standard deviation of X bar is going to be the standard deviation divided by what?
And
Kind of makes sense. I'm helping with this because, look, if you think of this and this goes over to there, it's kind of the same thing, isn't it? You're just not using the same standard deviation anymore, okay? Because this right here, this z-score, this is for the sample, okay? The z-score that you were using previously was for population. Population is whenever I know everything. Central limit theorem says what? You don't know everything. So what are we doing? We're taking a large enough sample of something that we're studying, pulling out some information and saying, because the central limit theorem states that if I take a large enough sample of something, when I do that, that will approach a normal curve, okay, which we like because we've done so much with normal curves right now. We like that because of that thing where it says, hey, well, one standard deviation says this, two standard, it's geometrically sound to us. So does that kind of make sense why we want to do that? Okay, and the larger the sample, the better things will get. I don't want you to get weirded out by that because that will change for you. Mainly because I'm going to start showing y'all some things here shortly where it basically says, hey, because you might say, well, if we have like the government, they do like some study, right? How come we can't just say, let's just study everybody? Believe it or not, the higher the number goes in your trials, whereas you might be becoming more exact over here, there's another problem that crops up over here. Okay, they actually call them type 1 and type 2 problems. Okay, you're gonna learn about them and we're gonna learn them and you're gonna say, I got it, and then I'm never gonna show it to you again. Okay? Because they're really hard to kind of grasp, and so I just kind of say these need to be addressed. But unless you go take a really high level statistics class, you don't ever gotta worry about them again. Okay? But they are there. And the number you're finding is actually the probability of that thing happening. Okay? Which is a good way of going. Remember when I said last class, I said, how do you know how much, is a good amount of trials, or in a polling, how many people should be studied? So continuing on with this one. Who this is, and either the sample size n is at least 30 or the population is normally distributed, then the standard score for the sample mean and the sampling distribution is given by that formula right there. Remember, because the central limit theorem says what? We have to have how many in our trial? What's the minimum? 30. If you have anything less than that, it doesn't work as well, okay? You haven't had enough, okay, to actually create anything of, I'm not gonna say value, I don't want to say that at all. Maybe due to dehydration or being sick, my vocabulary has shrunk dramatically, but still, it wouldn't be as trustworthy, let's just put it that way, and I will put that in quotations, okay? But we wouldn't consider it statistically viable at that point, okay? So you gotta go with these certain rules. And a lot of these, I'll be honest, in this class, it's sort of like one of those, you got to take it on faith by what I'm saying right now, because you could sit and go, well, why? Why 30? There is a mathematical reason behind it, okay? And it's not easy to prove, it's not, but it is provable, okay? But it's only provable through some very rigorous math at a higher level, okay? So it's one of those things of like, some surgeons become surgeons, they learn how to do heart surgery, right? But some surgeon out there actually learned how to do heart surgery. Does that make sense? Like, he created it, everyone else learned it. Okay, I'm not reinventing the wheel over here. That's kind of what most statisticians do. They don't reinvent the wheel, they're standing on the shoulder of giants. Okay, which is just fine. It's been proven. Okay. So that's kind of be how that works. Let me show you an example here, okay? According to the Centers for Disease Control and Prevention, CDC, the mean total cholesterol level for persons 20 years of age and older in the United States from 2007 to 2010 was 197 milligrams per deciliter. I have no idea what that means, but I say it confidently, so I sound smart. Okay? Because I'm not a biologist. Any of you taking biology, let me know exactly what milligrams per deciliter mean, and if that's a good or bad thing. Okay? But notice it gives us two questions here. Okay? What is the probability that a randomly selected adult from the population, hear that word, population, okay, will have a total cholesterol level less than 183 milligrams per deciliter? Use standard deviation of 35 milligrams per deciliter and assume that the cholesterol levels for the population are, important word, normally distributed. Because if they weren't normally distributed, do you know any other way in this class right now to do any sort of distribution other than normally distributed? No. Okay, so realize this is going back in time for you. We're not even using central limit theorem right now. We're just going to use our good old normal CDF, right? Like I said, let's look at A. Once again, I'm going to draw myself a little picture because a picture, what's that I was saying? Picture says 1,000 words. Okay. They do give me a mean of 197, and then they use a data point, an X value, right here of 183. My threes have been very funky this semester for some reason. It's like my brain goes, I don't like threes. And I'm never gonna let you write a normal one ever again without having to really think about it. Been that way all semester. I do not know why. Well, looking at this carefully, which direction am I gonna shade? Am I gonna shade to the right or to the left? To the left, exactly. I had a very good question before class. And if one person has it and is brave enough to ask, other people have had it, and you're chicken. No, I'm just joking. We all had it. This thing has a lower bound and an upper bound. Remember that this line right here, this bottom line, that's your x-axis. This right here is not zero, okay? Do not think of that as zero right there. Zero is way down the road somewhere, okay? You just got to remember, okay, that while that's the x-axis, that's still a real number line. So you can think of it like a real number line. And remember, real number line, when things go off to the left, they get smaller. When things go off to the right, they get larger. So this is shooting off, change this back to my pen. This is shooting off to the left, and so we're going off to negative infinity. Going the other direction, we'd be going positive infinity. So when you start putting these bounds in, you know exactly which one is which. And so we know we're going to start, we always start with our lower bound. We have to. Well, where are we coming from? Well, we're coming from negative infinity. Remember how you kind of wrote that in intermediate algebra? That was always kind of like your negative infinity with the parenthesis right there. Then it goes up to a certain point. Same, exact same methodology right now. Okay, so our lower bound, extremely large number, or your negative 1e to the 99, making sure you are using your negative key. Upper is going to be what? 183. Did you just combine both those into like one? Did you say 193 somehow in there? Okay. What's that standard deviation?
35.
Very good. I think I did it out of order. Still, what's our mean? Very good. And then it's easy enough right now. Just put your calculator right, run some calculations on it, and what are you going to get? First off, what decimal point am I going to? 4. Area under the curve is always a probability. Probabilities are always to 4 decimal places, okay? So when you get this done, you're gonna get 0.3446. Where get that for a number? Okay. So realize now, I want you to start remembering on your test, okay? It's gonna say, hey, give me the reasons. Okay? Why is this? What does this mean? Well, what is this saying?
Probability of a random selected adult has a lower or a cholesterol level less than 180.
And we're dealing with what? Population? Yeah. So it's, okay, I'm not gonna say it's exact, but come on. If I know everything about the population, how good is my probability on that? It's pretty good, wouldn't you say? I mean, hey, I've studied every last person out there. There you go. I've got this 34.46%. That's great. But there's a problem. We don't usually know everything about the population. Okay, so that's why we go to step 2. Look at B. Okay, they're going to give us the same exact information, but now we're getting to more real world. Okay. What is the probability that a randomly selected sample of 150 adults from the population will have a mean total cholesterol level of less than 183 milligrams per deciliter? And then once again, they use a standard deviation of 35. Well, now we've got to go back through and remember, let's do some review. What have we learned from the central limit theorem? It says 1, the mean is the same as what? Mean of the X bar, which means, what's our mean?
197.
Exactly, 197. And we need to know this information because we're gonna have to put this into our calculator here in a little bit. So we need to know the mean. Okay, well, then it says this, hey, you have a standard deviation now. Okay, well, what's our standard deviation? Can I just use the standard deviation like normal? No, because now standard deviation has changed. Whereas it could have been really, really large, right? With our population, that's not going to be the case anymore because now we've shrunken our number down into what? It's shrunk. It's not the population anymore, which could be billions of people. It's now shrunk to 150. So it's pulled it in by a whole lot. And so we have to use standard deviation is the same as the standard deviation of X bar, which is going to be all over the square root of n. And they give us a standard deviation, that's nice, of the population, which is 35. And then what is our square root? Exactly, 1/5. And here we always go to what?
2 decimal.
Very good, 2 decimal places. Which I think you should have got, what, 2.86? We're using the same exact graph, are we not? If we drew the picture, it doesn't look exactly the same now. We're gonna be coming in here. We got a mean right here. We've got this here. We've still got that, right? This is still gonna be the 183. This is still gonna be the 197. Correct? Our lower bound is still going off to negative infinity. Our upper bound is still gonna be the 183. Our mean is still the same. Really, the only thing that's really changed for us now is what? Standard deviation. So we got to put that in. Now, I did give you a new way to do a z-score. The reason I give you that, if you decide to use your table, what are you gonna have to do? Standardize it. That's why I gave you that really ugly formula in the beginning. That 183 you can't use. You're gonna have to take that 183 and standardize it if you choose to. Or just use your calculator. You're just fine doing a calculator. Your calculator doesn't need to standardize anything. Okay. So you come in here, you put everything back in, and you do once again the lower bound. I'm just gonna put the negative, Andy, you know what that means. Upper is going to be the 183. Mean of 197. Standard deviation of 2.86. You should get what? Get a really weird negative exponential value.
Yeah.
How about negative or 0 point? What about 6 zeros? Something like that. Or basically what? Yeah, that's the chance. Okay. You will be using the same stuff moving forward. But remember, now what you're doing, this is concept. This is all this is. This is concept. Like, what does this matter? By the population, looking at the population, we could say, hey, by the whole population, this is the odds. But if we just take a sample of only 150 people, there is a 0% chance that this many people are gonna have this type of, was it cholesterol level? Yeah, cholesterol level of this, okay? So we can infer, once again, infer, and that's what you're doing with statistics. You learn a little to learn about a lot. Okay? I harp a lot on social media sometimes, especially early on in class. But why do you think, let's say he's never been on social media ever, he's never got on one, and all of a sudden he gets a girlfriend, she's on it, she's like, man, I really wish you'd get on TikTok with me. Like it's been really hard this week because there's a guy posting stuff on TikTok and I won't let me watch it because I'm on TikTok, because I'll put this out there. I would rather have an STD than have TikTok because it's the same thing. Okay. And I've been really wanting to watch it, but I refuse to get TikTok. I'm not doing it. So I've tried to find people with it. So basically I can affect them and not myself, just sort of sin by proxy. But I'm I refuse to do it. So, but anyways, so he gets a girlfriend and she's like, hey, get on there, please, would you? He's like, all right, fine. So he puts on his information. He puts on very little information, but then all of a sudden he notices, man, this thing's giving me a lot of information. This is kind of cool. How does it know me so well? Why does it know him so well? Because of things like this. It doesn't need to know about a little, it doesn't need to know just about you. It knows about a lot of yous. Because while you are a very individual person, you are individual, down to your soul, you're an individual. But you are not that much of an individual when you take you and compare you to 7 billion other people. There's there's a statistical chance out there that there's someone out there that looks exactly like you. I mean, exactly like your doppelganger. You would never know that because did you know that if you ever look at someone else who looks exactly like you, you won't see it? Impossible. Other people will be like, whoa. Okay. But even identical twins will say they don't look the same. Because they can spot the differences. Okay. So there you go. That's what's happening. Central limit theorem says, I don't need to know a lot. Give me a little bit. So Facebook's not always sitting there going pulling all the information. It doesn't need to. It can just say, I'm going to take a little bit of a portion. And it's going to teach me a lot about, because it's going to demographic him. It's going, okay, age. It's going to see some likes, where you live, all kinds of stuff. It says, and around this area, where you live, where you go to college, we see this. And this is what comes out. And statistically, it's usually right. I say statistically. Is it perfect? Thing about it, though, when it gets it wrong, it corrects itself. Okay. And that's kind of the eerie part, is it's a self-correcting algorithm. So it's always learning about you. So think about that. So let's try this out. Let's try a few examples here. try to do this one really quick and tell me how you would do it. Work your way through it and see how you do. And then I will play catch up with you, okay? Because we're nearing closer and closer, edging our way toward the final. I want you to start having these practice sessions. Start looking at the question carefully. How are you gonna know what to do on the final? What's gonna be the, oh, this is what I need to look for, okay? Because here's the biggest problem with the final, is not trying to scare you, it's just so that it's a helpful guide. Every single question looks the same. Okay, except for like one. Okay, one question looks a little different. Okay, but other than that, you gotta be careful, okay? Keep working, you're still working on it. Good so far on that. You get that? You get 0.9 in your calculator, you should have got 0.9266953. Did you, yeah, so 0.9267, round to the fourth decimal place, okay?
Yeah.
Very good on that one now, you see, you get it now?
Mhm.
Okay. Everybody else good? I want to make sure you're getting the same. I get it. I'm not showing a lot of work. Pretty much it's now, are you getting the same thing right here on the calculator? That's the important thing, you know, and that's the blessing of doing statistics. You're like, man, I don't have to do a lot of work. But that's also the curse of statistics. I'm not doing a lot of work. You know, it's sort of like, you're not having to show a lot of calculation going, okay, where did I mess up? Well, it's not like in college algebra, you go, oh, I see, I forgot the negative. You know, and just one little simple rounding error changes things dramatically. You know, if you'd have put 0.61, it would have changed it, you know. Which is sometimes, while I will do that, did you see how I put this square root, the 4 over the square root of 42? You can put that in your calculator that way. It'll do the math that way for you if you don't want to work it all out. I'll be honest, I still get a little bit weirded out by doing that sometimes. I sometimes like to see the number there, so, yes, sir.
Whenever I do put it like in the square root form, it gives me 5138.
You're probably doing something weird with the parentheses. You gotta wrap things in a parenthesis sometimes. Okay, so kind of, you might have to take it and kind of wrap it. Okay. And that's one of the reasons right there, okay? And how would you know? I mean, just being honest, how would you know you got it wrong? You know, these numbers aren't as intuitive as you'd want them to be. You know, they really are not. And I said that day one of class, the numbers aren't intuitive. You can't just go, I mean, let's be honest. Is anybody in here going, yeah, 92 point, yeah, that sounds about right. Yeah, that's legit. You have no clue. I don't either. I couldn't tell you, like, yeah, that sounds. If I drew a perfectly accurate, you know, picture, maybe I could go, yeah, that looks good. My picture is not anywhere near accurate. That doesn't look like 92% covered in. I just drew a picture to tell me, hey, here's my lower, here's my upper, let's go at it. That's what that was helping me with. Nowhere near was that thing just like, oh, let me go in here, let me spend the time doing that. No, I'm looking just for a picture to give me a guiding light on how to do things, okay? Let's do another one. Calculate the z-score. Ooh, z-score. Because it is good. Some people want to use the tables. I am not against using the table because really the table works just about as fast, you know, as your calculator at times. Okay? What's your old definition for a z-score? I'll help you derive this, so you don't even have to memorize it, because I don't think I think I give you the z-score, but just in case, let's say I don't. What is your old definition of a z-score? Remember for a population, what was it? It was z what?
X
Minus
U.
divided by. Okay, well, let's think about it. We've changed some of the definitions here, haven't we? Everything up there is exactly the same except for one thing. Yeah, what's our new definition of a standard deviation?
Standard deviation divided by.
Heard of that, right? So why don't we just take this and put that there? Because the mu is what? It's still the same, right? It's still just the mu of the x bar, so nothing's really changed there. So we can just say this, let's change this as to z. Our x is gonna change now because now that's just gonna be our x bar minus the mu,
Let's see.
all divided by the standard deviation. Square root of n. And there you go. Now you have something. that you can play with. Our X bar is going to be 53. When you're dealing with Z-score, what do you round to?
2 decimals.
2. Thank you. And this is what's good about kind of at least, here's a little hint. Even if you don't want to use your table, if you'll at least get an idea of what it looks like, that almost tells you exactly what to round to. Because think of what your table looks like. It rounds to 2 on the perimeter, it goes to 4 on the inside. And so that kind of tells you, okay, I know what I'm rounding to. If it's Z, I'm looking at the perimeter, 2. If it's going toward the inside, it's 4. Okay, at least it kind of gives you an idea. Okay, and so this one, since it's going to be 2, we're going to be rounding to 1.68.
Whenever we find the square root, we round to 2 as well, right?
I keep everything together. I would have done 53 minus 50 divided by parenthesis 12 divided by the square root of 45 and put parenthesis. Because that is the problem, doing some of this, doing too much in your calculator all at one time. Your calculator has got a really. And I'm gonna be honest, guys, I got really good at what got me good at my calculator is actually taking a programming class. And that because computers are wonderful, but they're not as smart as you think. They're amazingly stupid. And I didn't know that until I started like programming. Okay, that you literally have to tell it, hey man, you need to bypass this because I see what you're trying to do, but you're doing the very wrong, you're doing PEMDAS wrong. Okay, it's sort of like most math to teachers. Okay, and it says because I say PEMDAS, it's mainly PEMDAS. Your calculator's trying to do PEMDAS weird. Okay, and if you don't start putting things in, it's very like literal. It needs parentheses a lot. Okay, it needs a lot more parentheses that you would use in it needs more parentheses than you'll ever need in your normal day. Okay, and so you just kind of got to get used to that. Like my rule of thumb with calculator is, especially with fractions, parentheses on the top divided by parentheses on the bottom. That means you're literally jumbling everything inside parentheses if you want to try to put everything in together that way. Okay, so just be real careful with that. Did that help you out on that one?
No, it doesn't give me like the same answer.
Did everybody else get 1.68 on that one? Okay. Did you do 53 minus 50? When you do 12 divided by the square root of 45, do you get 1.79? When rounded, or 1.788?
Yeah.
Okay, so do 3 divided by 1.788. Yeah. That's what I'm saying. Sometimes rapid.
You can put like the whole thing like that.
You can if you want, but if you're gonna do that, literally, I would do this right here. Parenthesis around this, and then notice then you put the divide sign and then put parentheses around the bottom too. Or do it separately. I do it this way, 53 minus 50 gives me a 3. Now put 3 divided by parentheses 12 divided by the square root of 45. Then you're gonna have to probably close off 2 sets of parentheses on some calculators. Because you notice how your square root sometimes will give you that little open parenthesis. I don't know if y'all's does that, but sometimes it'll give you an open parenthesis. You need to close off both of them. So just kind of keep an eye on that. One more. And then we're going to move on to 7.3. This one's a little bit different. Look at it carefully. The standard deviation of the scores on a skills evaluation test is 421 points with a mean of 1,728 points. Nice. If 309 tests are sampled, hint, hint, Sampled means we're not dealing with what anymore? Population. This is kind of a hint for your final. Everything I'm gonna be doing now is going hint, because I don't want you to look at the file and go, oh crap. No, I want you to know that, dude, I got this, okay? Hey, little spoiler alert, okay? 60% of your questions, maybe a little bit more, okay? Normal CDF, there's your button. Isn't that kind of what we've been using the whole time? Normal CDF, normal CDF, normal CDF. The hard part is remembering, am I dealing with a population or am I dealing with what? Exactly. And here in a little bit, when we start dealing proportions, there's another button. And you'll know, oh, look, how do I know I'm dealing proportions? Oh, the percent. It's telling me right there, percent. There it is, okay? So just kind of heads up, okay? If 309 tests are sampled, what is the probability that the mean of the sample would differ? Hear this word. Differ from the population mean by less than 36 points. Hear what that's saying. It's not saying less than, it says differ by less than. Let me give you a hint what that means. Differs by less will look like this. I'm just going to give you an arbitrary. You have a mean, right? Differs by less looks like this. Differs by more would look like this. So less and then more. Differs by less, differs by less than, you're inside that, okay? If arbitrary number, if I have 100 points, differing by less than 30, which would mean by this, I can go to 70 and it's gonna be less than that. I can go to 130 or it's gonna be less than that. It's differing by less than that number. But it differs by more, that means it's outside that number. It's gone further than that number. Okay? And if you still can't wrap your head around that, you want a little hint? Memorize that. Happy birthday. Obviously, though, every single one of you, and I know every single one of you because every single one of you is extremely smart. You can also tell that this is also going to be what now? Something that's not going to have your normal bounds, isn't it? It's going to be bounded. Okay, so let's take a look here. And I'm going to do this in two ways. We're going to do it the exact way, and then I'm going to show you the opposite way, just in case you see one, okay? So once again, we have a mean. Will somebody give me the mean of the X bar, please? 1728, thank you. My standard deviation they give me is 421. We know we can't use that because we're dealing with a sample. That tells me I've got to use that other little equation here. So I'm going to go mean of the sample is going to be 421 divided by the square root of
309.
309. Very good. And then I should get what there? Is it 95?
Yeah.
Yeah. 23.95. And then we just start saying, okay, how are we going to put this in? Well, we know we have an upper, we know we have a lower now. Okay. Here is the thing. But notice, you got to find some bounds. No longer do you have negative infinity, no longer do you have positive infinity, but you do have this. You can say, hey, we're still looking for area, right? We've got a mean here. We've got a number here, a number here. Our mean is 1,728. But then it's going to do what? It's got to be less than 36 from that. So why don't we plus or minus 36 from that? That gives us those bounds we are looking for. Because when we do that, notice we're going to get 1692 and 1764. Does that make sense what I just did? And then that's going to be the bound I'm going to be in between. I have a lower bound, I have an upper bound now. Okay, so my lower once again, 1692. Upper 1764. Mean of 1728, and then we got that standard deviation of 23.95. Run everything in your calculator, what do you get? Round to how many decimal places?
4,
Or what are we gonna get?
86, 0.8672.
Very good, 0.8672. Here's a question. What if it said more than?
If it's just more than we just add, we wouldn't subtract, right?
Or you just subtract it. Line one, minus one.
Here's what it said. Few ways to do it. One. Okay, and I'll just kind of like point this out. In fact, let me point out in blue so that way you don't confuse anything here. One way, find the complement, just like you just said, okay? Literally, if I said the word more than, okay, right here. Literally, you could have still said, well, I'm gonna bound this guy right here, and then I'll just find the complement. That works, right? Or we know normal curves are what? Starts with the S. They're symmetrical. Couldn't I have just found one of those? Exactly, and then multiplied by 2. Right? One of them would have gone up to negative infinity, and then I would have found up to that point and did the area, and then multiplied that by 2. It's really up to you. That's why we like normal curves, because there's a lot of ways we can do the math. Okay? So just kind of have a little hint. If you do see more than, you will on your homework. Okay? You can come here and go, oh, okay, well, I can bound it into 1 minus, or just do one part of it and then multiply by 2. Okay? Good?
So with that side, would it be 0.1328?
If you did 1 minus,
Yeah,
yeah, well, not that one side. Okay, if you do 1 minus,
and then divided by.
you have to divide by 2. Yeah. And it'll never do that. It'll never just say one side on something like this one. Because this is a differing question. Okay, it's saying difference from the mean, which is why you've got some tails happening. If I were just going to show you one tail, I would say the word less than. That makes more sense, or greater than. And I would give you an automatic bound starting either at negative infinity or some bounding going to somewhere. Okay, so look for that word. So some special words to look for this before we move on. Differ. Okay, look for that word, differ. And then as we step away from this one and move on to the next lesson, remember that right there. Look for, realize where they're transitioning you from population and then they're going what? But samples, okay? They'll start off talking about population, but then they're going to get to saying samples. I need you to start seeing that, and hopefully maybe there should be someone in here probably saying to themselves, there's always one. Hey, how would you get the standard deviation? You need to know what? How did they get the standard deviation of population? You have to know the population. That'll plant that little seed, because that should make you go, well, why are we doing this anyway if we already know the standard deviation and the mean of the population? Well, that's going to change. Because that's not really accurate, because if I know the standard deviation and the mean of the population, that means I know the mean and I know the population. I don't need all this information, okay? All right. Let's start. We're going to start 7-3. 7-3 will actually go kind of quick. The notation is going to look ugly, and unfortunately, this is going to be one of those, calculator doesn't do it for you, you're going to have to do it. You're still going to be using normal CDF. Yes, I think I was like, are you? Central limit theorem with proportions. I'm going to start this one out I said, we're not gonna get very far, okay? I'll probably get through the animations. Because I need you to really see what you are seeing as we kind of do things. So now we moved on from means. And now we're gonna start dealing with proportions. Remember, you hear the word proportion, I literally want you to think percentages. Okay? That's literally what I want, because not, I really don't want you to think that because of anything special, other than the fact that it is. It's percentages, a percentage of something. Okay, but instead of it being a percentage of a population, we're now gonna start taking what? Samples from that population. Okay? Notice, I have myself a population of people here. I did all the animation myself on this, thank you very much. But when y'all start seeing this, go, wow. If I ever need help on a PowerPoint, I'm gonna contact my math. I love PowerPoint. I watch YouTube videos over PowerPoints on how to do PowerPoints and Excel videos. My wife tells me all the time, she goes, I am never worried about you cheating on me. You shouldn't. She's gotten up at 2 o'clock in the morning, I'm in the bathroom, she's like, what are you doing? I'm using the restroom and look at this video I found over PowerPoint. She's like, I love you, I'm going back to bed. Well, look at this. I did that. Okay, I did that with Word. No special stuff, okay? I took a sample, okay, of people. My sampling was like, what are the proportion of people wearing black pants? That seems to be my thing this semester. What are the proportion of people wearing black pants? Well, if I knew the population, I could literally say this, right? You've done this, the total number of outcomes, right? But then the proportion is gonna be what? What am I looking for compared to the number of outcomes? The number of outcomes is how many people is in this picture. I don't know how many people are in that picture. Say 100. And if I knew the population, I could say 40 people out of 100 people, so 40% had black pants. But what I did was what? I took a sample, okay, and said, okay, well, this many people of my sample are what? Wearing black pants. So I can infer that this many people out there are what? Wearing black pants. Does that kind of help you kind of see kind of where this lesson is probably going? Sort of the same as what you just did, right? I don't know this information, but I can take a sampling of it and get an idea about what's happening with the population. That's all the central limit theorem is doing. And it's what you're going to keep doing over and over and over again. Okay? So notice, once again, you can find proportions like this. So, come here, population proportion, and then you got sample proportion. So what do you got here? We got a population proportion of P is equal to X over, look at that capital letter N. We know what that is, right? That's going to be what? Capital letter N is always population. But we have another little terminology here. We've got P hat. Okay? There you go, right there. Things seem a little larger. P hat. Okay, sometimes they'll call that thing a caret. That seems to become the terminology nowadays. I don't like that because my old statistics teacher who I had at this college, when I very first took statistics, she called it hat and she passed away. And so therefore it will be called hat until I pass away. Okay, that's sort of a remembrance. I also kind of remember it because it helps me out. Kind of cool like that. See? I did it. See, that's kind of cool, huh? Anyways, P hat, see? Pretty gangster. Anyways, population. Look at the video and maybe it'll help you out. We have a population of marbles, right? Look at how this works. We take a sample. That's it. It's like having a jar. And you do what? You have like a jar of like Skittles. Okay. And you reach your hand in, you pull some out, and you're gonna eat some. Don't be like my wife and pick out certain colors. I know I married a psycho. Okay. I love her to death. She's a psycho. She'll like pick out colors. I'm like, what are you doing? They all taste the same. She's like, no, yellow tastes different. I'm like, no, it doesn't. It tastes like a Skittle. Okay. Do some of y'all think they taste differently? You wouldn't know. We should test that theory. Have you ever been blindfolded and like, let me just hand you a red one, see like, oh, that tastes like red. Okay, no, you won't know. Okay. But look, that's literally how it just happened. I reached in, I grabbed some, I pulled it out, there you go. Okay? Works the same way. Look at this right here. We got a sample, they pull it out, and there you go. Now we know the sample says this. So we can infer, what do you think? How many red balls are there? Probably total, not total, proportionally. We can say that we think, don't ever say the words we know. Okay, get that out of your head right now. And I say that because of where we're going here pretty soon. This in the hypothesis testing, you're gonna think, just trust me. I don't want to start muddying the water right now. You don't ever know anything in statistics. Okay. The more data you have, the better you can be probably right. Okay, but until something happens, like you can go, you know what, there's very low percentage that the sun's gonna blow up. And then it does, you're like, oh, I was wrong. You know, still. Look at this one. One, all you're doing, you're drawing samples from a population, and you can keep doing it over and over and over again. Isn't that what the central limit theorem says? That if I keep taking all the possible samples and just keep drawing them over and over, remember that one when I showed you, it says, if we could take all the possible samples, that would approach what? A normal curve again. That's exactly what the central limit theorem says, and it works the exact same way with proportions as well, okay? And the reason you need to just take it on faith until you take like a master's level statistics class, just go, yeah, okay. That means the formulas I'm about to show you, when you start doing the statistical work with these formulas, you go, yeah, that works. Because if I did this to infinity, or all the possible combinations thereof, okay, then this will work. Because notice I'm just drawing 6 out. I don't know what's in their actual population here, but if I did, you know, 100 choose 6 and did all of the possible samples that I ever could, it's going to approach what? That normal curve that we're looking for. And that's what we want. We want things to approach that normal curve. So, remember the properties of binomial, okay? You're gonna hear this a lot. Anytime you're dealing with a proportion, you gotta go back to that binomial theorem, okay? That says this, you gotta have a fixed number of trials, okay? Things can't be shooting off to infinity, okay? Each trial is independent, okay? We know what that means now, independent. Remember, this proportion has no effect on the next, okay? Remember that conditional probability that you learned? For each trial, there are only 2 possible outcomes, success and failure. Be real careful. Remember, I've been saying it every time. Success is dependent upon what the question asks. And sometimes, you've already all ran into this, where they start the question off this way. But then right there at the very end, they throw a curveball. You know, they'll say, hey, what's your, you know, you believe that there's this much of a chance of you making this many right questions, whatever. And then right there it says, what's your probability of missing them? It changed it right there at the end. Okay, so your idea of success is actually missing something. Okay, so just remember how we gauge success and failure. If you're trying to decide on the death rate of something, unfortunately, your idea of success is people dying. Okay, so be careful, don't get hung up on that success and failure. For every trial, there's a success called P, the probability of getting a failure is 1 minus P, they complement, okay? And then the binomial random variable X counts the number of successes in trials. And then they're going to give you the formula. They, me, whoever you want to blame it on. Once again, just like you did in the last one, okay? Notice instead of U of X bar equaling U, we're not dealing with a mean anymore, are we? What are we dealing with? Proportion. We're dealing with a proportion. Okay, a probability. Okay? So that P is always going to be, instead of a mean, we're dealing with proportions. So U, okay, is going to equal to P. So when they give you that proportion, that's going to be your mean. And they're either going to give you a proportion or they're going to give you a way to calculate for it. Remember how you calculate for proportions? Total number of outcomes divided by your what you would like to see. Okay? Your frequency. And then there's your standard deviation. Yes, you will be given this on your test. Like I'll give you the formula, okay? And since I'm letting you do your test in Hawks, remember Hawks does give you formulas, I believe. I'm gonna be double checking this thing a lot. I still think on your test, I've already ran through it a couple of times, but I always let other people run through. And the reason I went back to Hawks is there was too many like little things happening in the last test that shouldn't have happened. They were corrected long before that test was ever loaded. And Canvas messed up and I didn't like it. So I was like, let's go back to Hawks, because then I can just blame Hawks. Because our rip's coming too, and I can blame him to his face. So one more thing, if you decide you want to use the table, which I'm all for, I use the table a lot, okay? There is if you need to standardize it, okay? Notice if you want it, okay? Now, I do believe right here would be a good place to kind of stop. We'll stop here. When you come back in on Thursday, we'll run through some examples, okay? And then we're gonna get started on 8.1, okay? Yes, 8.1, I was thinking, I was like, we're done with 7? I do believe, correct me if I'm wrong, you should, because we are now gonna be done with chapter 7 this week. Probably next week, I do believe you will have a chapter 6, 7 test. And I think a discussion opens up this week. Okay? Be careful about that. Also, it would behoove you to start looking at that project I have coming up for you. Not the project, but remember that little paper I showed you on the module page? Start looking at that. Okay, because we're getting into some areas where you might be able to start noticing some of the math going on. Okay? Or decide which one you want to do. And you can either have it out, you kind of start working on it or looking at it and kind of digesting on it, okay? All right, guys, I'll see y'all guys later.
Together.